A generator is subjected to electrical stresses imposed on the insulation of the machine, mechanical forces acting on the various parts of the machine, and temperature rise. These are the main factors which make protection necessary for the generator or alternator. Even when properly used, a machine in its perfect running condition does not only maintain its specified rated performance for many years, but it does also repeatedly withstand certain excessive overload. Preventive measures are needed to protect machines from overloads and abnormal conditions. Despite efficient design, construction, and operation, faults can't be entirely avoided. Generator protection devices quickly eliminate faults when they occur. Generators can face internal or external faults. Since generators are connected to electrical power systems, any fault in the system must be quickly cleared from the generator to prevent permanent damage. Generators can have many types of faults, so multiple protective schemes are used. These schemes include both discriminative and non-discriminative types. Coordinating systems and settings is crucial to ensure sensitive and selective generator protection. Types of generator protection. The various forms of protection applied to the generator can be categorized into two manners: protective relays to detect faults occurring outside the generator. Protective relays to detect faults occurring inside the generator. Other than protective relays, associated directly with the generator and its associated transformer, there are lightning arresters, overspeed safeguards, oil flow devices and temperature measuring devices for shaft bearing, stator winding, transformer winding and transformer oil, etc. Some of these protective arrangements are of non-trip type, i.e. they only generate alarm during abnormalities. But the other protective schemes ultimately operate master tripping relay of the generator. This should be noted that no protective relay can prevent fault, it only indicates and minimizes the duration of the fault to prevent high temperature rise in the generator, otherwise there may be permanent damage in it. It is desirable to avoid any undue stresses in the generator, and for that it is usual practice to install surge capacitor or surge diverter or both to reduce the effects of lightning and other voltage surges on the machine. The protection schemes usually applied to the generator are discussed here below in brief. Protection against insulation failure. The main protection provided in the stator winding against phase-to-phase or phase-to-earth fault is longitudinal differential protection of generator. Second most important protection scheme for stator winding is interturn fault protection. This type of protection was considered unnecessary in previous days because breakdown of insulation between points in the same phase winding, contained in the same slot, and between which a potential difference exists, very rapidly changes into an earth fault, and then it is detected by either the stator differential protection or the stator earth fault protection. A generator is designed to produce relatively high voltage in comparison to its output, and which therefore contains a large number of conductors per slot. With increasing size and voltage of the generator, this form of protection is becoming essential for all large generating units. Stator earth fault protection. When the stator neutral is earthed through a resistor, a current transformer is mounted in the neutral to earth connection. Inverse time relay is used across the CT secondary when the generator is connected directly to the bus bar. In case of generator feeds power via a delta star transformer, an instantaneous relay is used for the same purpose. In the former case, the earth faults relay is required to be graded with other fault relays in the system. This is the reason why inverse time relay is used in this case. But in the latter case, the earth fault loop is restricted to the stator winding and primary winding of the transformer, hence, there is no need of grading or discrimination with other earth fault relays in the system. That is why instantaneous relay is preferable in the case. Grounding techniques. Question is, why ground? It improved safety by allowing detection of faulted equipment, stop transient overvoltages, notorious in ungrounded systems, ability to detect a ground fault before a multiphase to ground fault evolves, if impedance is introduced, limit ground fault current and associated damage faults, provide ground source for other system protection, other zones supplied from generator. Types of generator grounding: low impedance, good ground source. The lower the R, the better the ground source. The lower the R, the more damage to the generator on internal ground fault. Can get expensive as resistor voltage rating goes up. Generator will be damaged on internal ground fault current typically 200 to 400 A. Types of generator grounding: high impedance, creates unit connection, system ground source obtained from GSU, uses principle of reflected impedance, RNGR equal Neutral grounding resistor resistance, RR equal reflected resistance, ground fault current typically greater than 10A, types of generator grounding, compensated, creates unit connection, most expensive, tuned reactor, plus GSU and grounding transformers, system ground source obtained from GSU, uses reflected. Impedance from grounding transformer, same as high impedance grounded system does, generator damage mitigated from ground fault, reactor tuned against generator capacitance to ground to limit ground fault current to very low value can be less than 1A, hybrid impedance grounding, has advantages of low Z and high Z ground, normal operation. Low Z grounded machine provides ground source for other zones under normal conditions, 51G acts as backup protection for uncleared system ground faults, 51G. Is too slow to protect generator for internal fault, ground fault in machine, detected by the 87 GD element, the low Z ground path is opened by a vacuum switch, only high Z ground path is then available, the high Z ground path limits fault current to approximately 10A stops generator damage. Rotor earth fault protection, a single earth fault does not create any major problem in the generator but if the second earth fault has occurred, however, part of the field winding will become short-circuited and resulting in unbalanced magnetic field in the system and consequently there may be major mechanical damage to the bearings of the generator. There are 3 methods available to detect the types of fault in the rotor. The methods are potentiometer method, AC injection method, DC injection method. Generators experience shorts and abnormal electrical conditions, proper protection can mitigate damage to the machine, proper protection can enhance generation security, generator protection, short circuits in the generator, uncleared faults on the system, abnormal electrical conditions may be caused by the generator or the system, short circuits, in generator, phase faults, ground faults on system, phase faults, ground faults, abnormal operating conditions, abnormal frequency, abnormal voltage, overexcitation, field loss, loss of synchronism, inadvertent energizing, breaker failure, loss of prime mover, blown VT fuses, open circuits conductors, stator ground fault. Traditional stator ground fault protection schemes include neutral over voltage, various third harmonic voltage dependent schemes. These exhibit sensitivity, security and clearing speed issues that may subject a generator to prolonged low-level ground faults that may evolve into damaging faults. Unbalanced stator loading protection. Unbalancing in loading produces negative sequence currents in the stator circuit. This negative sequence current produces a reaction field rotating at twice synchronous speed with respect to the rotor and hence induce double frequency current in the rotor. This current is quite large and causes overheating in the rotor circuit, especially in the alternator. If any unbalancing occurred due to fault in the stator winding itself, that would be cleared instantaneously by the differential protection provided in the generator. If the unbalancing is occurred due to any external fault or unbalanced loading in the system, it may remain undetected or may persist for a significant period of time depending on the protection coordination of the system. These faults then be cleared by installing a negative phase sequence relay with the characteristics to match the withstand curve of the machine. Protection against stator overheating. Overloading can cause overheating in the stator winding of the generator. Not only overloading, failure of cooling systems and insulation failure of stator laminations also cause overheating of the stator winding. The overheating is detected by embedded temperature detectors at various points in the stator winding. The temperature detector coils are normally resistance elements which form one arm of the Wheatstone bridge circuit. In the case of smaller generator normally below 30 megawatts, the generators are not equipped with embedded temperature coil but are usually fitted with thermal relay and they are arranged to measure the current flowing in the stator winding. This arrangement only detects overheating caused by overloading and does not provide any protection against overheating due to failure of cooling systems or short-circuited stator laminations. Although overcurrent relays, negative phase sequence relays, and devices for monitoring constant flow are also used to provide a certain degree of thermal overload protection. Why do we care about faults near neutral? A fault at or near the neutral shunts the high resistance that saves the stator from large currents with an internal ground fault. A generator operating with an undetected ground fault near the neutral is at accident waiting to happen. We can use third harmonic or injection techniques for complete 100% coverage, generator capacitance, and third harmonics. Third harmonics are produced by some generators, amount typically small, lumped capacitance on each stator. And is CS divided 2. CT is added at terminal end due to surge caps and isophase bus, effect is third harmonic null point is shifted toward terminal end and not balanced, develops in stator due to imperfections in winding and system connections, unpredictable amount requiring field observation at various operating conditions, also dependent on pitch of the windings, which a method to define the way stator windings placed in the stator slots, using third harmonic in generators, generator winding in terminal. Capacitances C provide path for the third harmonic stator current via grounding resistor. This can be applied in protection schemes for enhanced ground fault protection coverage. A fault near the neutral shunts the third harmonic near the neutral to ground. Result is a third harmonic undervoltage, security issues with generator operating mode and power output real and reactive, stator ground fault, high Z grounded machines 95% stator ground fault provided by 59 and tuned to the fundamental frequency, must work properly from 10 to 80 Hz to provide protection during startup. Additional coverage near neutral last 5% provided by 27 TN, third harmonic undervoltage, 59D, ratio of third harmonic at terminal and neutral ends of winding, full 100% stator coverage by 64S, use of subharmonic injection, may be used when generator is offline, immune to changes in loading MW, MVR, directional neutral overcurrent, 67N low Z grounded generator, 67N element provides selectivity on multiple. 67N is set faster than 51N, may be short definite time delay, ground current should not flow into a generator under normal operating conditions, may be applied on ungrounded machines for ground fault protection if bus or other generators are a ground source. Directional neutral overcurrent, 87G, low Z grounded generator, 87GD element provides selectivity on multiple bus machine applications, requires phase CTs, or terminal side zero sequence CT, and a ground CT. 87GD uses currents with directionalization for security and selectivity. 87GD is set faster than 51N, may use short definite time delay. Ground current should not flow into a generator from terminal end under normal operating conditions. Ground current should not flow unchallenged into machine. Improved ground fault sensitivity 87GD, direction calculation used with currents over 140 mA on both sets of CTs 3I0 and IG, directional element used to improve security for heavy external phase-to-phase faults that cause saturation. When current greater 140 mA, element uses current setting and directional signal. When current smaller 140 mA, element uses current setting only. Saturation will not occur at such low current levels. Directional signal not required for security. Allows element to function for internal faults without phase output current. Open breaker, internal fault source by generator only. Field rotor ground fault. Traditional field rotor circuit ground fault protection schemes employ DC voltage detection. Schemes based on DC principles are subject to security issues during field forcing, other sudden shifts in field current and system transients. Field rotor ground fault 64F. To mitigate the security issues of traditional DC-based rotor ground fault protection schemes, AC injection-based protection may be used. AC injection-based protection ignores the effects of sudden DC current changes in the field rotor circuits and attendant DC scheme security issues. Advanced AC injection method. Advantages. Scheme is secure against the effects of DC transients in the field rotor circuit. DC systems are prone to false alarms and false trips, so they sometimes are ignored or rendered inoperative, placing the generator at risk. The AC system offers greater security, so this important protection is not ignored or rendered inoperative. Scheme can detect a rise in impedance which is characteristic of grounding brush liftoff. In brushless systems, the measurement brush may be periodically connected for short time intervals. The brush liftoff function must be blocked during the time interval the measurement brush is disconnected. Stator phase faults 87G phase differential primary for in-zone faults. What goes into zone must come out. Challenges to differential, CT replication issues, permanent flux causing saturation, DC offset desensitization for energizing transformers and large load pickup, must work properly from 10 Hz to 80 Hz so it operates correctly at off-nominal. Frequencies from internal faults during startup may require multiple elements for CGT static start. Tactics, use variable percentage slope, operate over wide frequency range, uses IRMS-IFN to adaptively desensitize element when challenged by large DC offset in harmonics for security. DC offset can occur from black starting in close-in faults. Negative sequence current, typically caused by open circuits in system, down conductors, stuck pole switches and breakers. Unbalanced phase currents create negative sequence current in generator stator and induces a double frequency current in the rotor. Induced current 120 Hz into rotor causes surface heating of the rotor. Negative sequence electromechanical relays, sensitivity restricted and cannot detect I2 levels less than 60% of generator rating. fault backup provided, generally insensitive to load unbalances or open conductors. Negative sequence digital relay protects generator down to its continuous negative sequence current I2 rating versus electromechanical relays that don't detect levels less than 60%. Fault backup provided, can detect load unbalances, can detect open conductor conditions. Overexcitation measured, high volts by Hertz ratio, normal equal 120 V by 60 Hertz equal 1 pu. Voltage up, and or frequency low, make event, issues, overfluxing of metal causes localized heating, heat destroys insulation, effects. Generators and transformers. Generator voltage regulator problems, operating error during offline manual regulator operation, control failure, VT fuse loss in voltage regulator AVR sensing voltage, system problems, unit load rejection, full load, partial rejection, power system islanding during major disturbances, Ferranti effect, reactor out, capacitors in, runaway LTCs, protects machine against excessive V by Hertz overfluxing legacy protection, typically stair-step 2 definite time set points, 2 definite time elements. One may be used to alarm, one may be used for high set fast trip, either overprotects or underprotects, instantaneous reset. Modern protection, definite time elements, curve modify, alarm, inverse curves, select curve type for best coordination to manufacturer's recommendations, employ settable integrating reset, provides thermal memory for repeat events, V by Hertz measurement operational range, 2 to 80 Hz, necessary to avoid damage to steam turbine generators during rotor pre-warming at startup, necessary to avoid damage to converter start gas turbine generators at startup, in both instances, the generator frequency during startup and shutdown can be as low as 2 Hz, an overvoltage 59 function, designed to work properly up to 120 Hz, is important for hydro generators where the generators can experience high-speed high-frequency during full load rejection. Since the V by Hertz during this condition is low, the 24 function will not operate, and the 59 function will provide proper protection from overvoltage. Loss of field can adversely affect the generator and the system. Generator effects, synchronous generator becomes induction, slip-induced eddy currents heat rotor surface, high reactive current drawn by generator overload stator, power system effects, loss of reactive support, creates a reactive drain, can trigger system area voltage collapse. Generator capability curve, limiting factors are rotor and stator thermal limits. Underexcited limiting factor is stator end iron heat, excitation control setting control is coordinated with steady state stability limit. Minimum excitation limiter MEL prevents exciter from reducing the field below SSSL. Positive sequence quantities used to maintain security and accuracy over a wide frequency range. Must work properly from 50 to 70 Hz or 60 Hz systems. Required to operate correctly and not misoperate with wide frequency variations possible during power swing conditions. May employ best of both methods to optimize coordination. Provide maximum coordination between machine limits, limiters and protection, offset MO for Z1. Fast time for true loss of field event. Impedance with directional unit and slower time for Z2. Better match of machine capability curve. Also able to ride through stable swing. May employ voltage supervision for accelerated tripping of Z2 slower zone in cases of voltage collapse where machine is part of the problem, importing VARs. Phase distance backup protection may be prone to tripping on stable swings and load encroachment, employ 3 zones. Z1 can be set to reach 80% of impedance of GSU for 87G backup. Z2 can be set to reach 120% of GSU for station bus backup or to overreach remote bus for system fault backup protection. Load encroachment blinder provides security against high loads with long reach settings. Z3 may be used in conjunction with Z2 to form out-of-step blocking logic for security on power swings or to overreach remote bus for system fault backup protection. Load encroachment blinder provides security against high loads with long reach settings. Use minimum current supervision provides security against loss of potential machine offline, generator out-of-step protection, types of instability, steady state, steady voltage and impedance load flow, transient, fault, where voltage and impedance change rapidly, dynamic, oscillations from AVR damping usually low F, occurs with unbalance of load in generation, short circuits that are severe in close, loss of lines leaving power plant raises impedance of load flow path, large losses or gains of load after system breakup, generator accelerates or decelerates, changing the voltage angle between itself and the system, designed to cover the situation where electrical center of power system disturbance passes through the GSU or the generator itself, more common with modern EHV systems where system impedance has decreased compared to generator and GSU impedance. When a generator goes out of step synchronism with the power system, high levels of transient shaft torque are developed. If the pole slip frequency approaches natural shaft resonant frequency, torque produced can break the shaft. High stator core and iron flux can overheat and short the generator stator core, GSU subjected to high transient currents and mechanical stresses. Low vacuum protection. This protection usually is in the form of a regulator which compares the vacuum against atmospheric pressure. It is normally fitted to the generator set above 30 megawatts. The modern practice is for the regulator to unload the set via the secondary governor until normal vacuum conditions are restored. If the vacuum conditions do not improve below 21 inch, the stop valves are closed and the main circuit breaker is tripped. Protection against lubrication oil failure. This protection is not considered essential since the lubrication oil is normally obtained from the same pump as governor oil, and a failure of the governor oil will automatically make stop valve to close. Protection against loss of boiler firing. Two methods are available for detecting the loss of boiler firing. In the first method, normally opened NO contacts are provided with the fan motors, which may trip the generator if more than two motors fail. The second methods use a boiler pressure contacts which unload the generator if boiler pressure falls below approximately 90%. Protection against prime mover failure. If the prime mover fails to supply mechanical energy to the generator will continue to rotate in motoring mode. That means it takes electrical energy from the system instead of supplying it to the system. In a steam turbine, the steam acts as a coolant, maintaining the turbine blades at a constant temperature. Failure of the supply will therefore result in overheating due to friction, with subsequent distortion of turbine blades. The failure of steam supply can cause severe mechanical damage in addition of imposing a heavy motoring load on the generator. Reverse power relay is used for this purpose. As soon as the generator starts rotating in motoring mode, the reverse power relay will trip the generator set. Overspeed protection. While it is the general practice to provide mechanical overspeed devices on both steam and hydro turbine, which operate directly on the steam throttle valve or main step valve, it is not usual to back up these devices by an overspeed relay on steam-driven sets. It is, however, considered good practice on hydroelectric units, as the response of the governor is comparatively slow and the set is more prone to overspeed. The relay, when fitted, is usually supplied from the permanent magnet generator used for the control of governor. Protection against rotor distortion. The cooling rates following shutdown, at the top and bottom of the turbine casing, are different, and this uneven temperature distribution tends to cause destruction of the rotor. To minimize the disruption, it is common practice to turn the rotor at low speed during the cooling down period. In the view of the forces involved with large modern rotor, it is now standard practice to fit shaft eccentricity detectors. Protection against difference in expansion between rotating and stationary parts. During the running up period, the rate of heating of the rotor differs from that of the casing, due to the difference in mass. As a result, the rotor expands at a different rate to the casing, and it is necessary to overcome this unequal expansion. To this end, proposition is made on the larger machine for independent supplies of steam to be set to certain joints on the casing. It is desirable, therefore, to provide a means of measuring the axial expansion to assist the operator to feed the steam to the correct points, and also to provide indication of any dangerous expansion. The shaft axial expansion detector is basically similar to the equipment described for rotor distortion equipment, except that the detector magnets are fixed to the turbine casing. Protection against vibration. Vibration detectors are usually mounted on the bearing pedestals. The detector consists of a coil mounted on springs between U-shaped permanent magnets. The voltage output from the coil, which is proportional to the degree of vibration, is passed from the coil into integrating circuits and then into interval indicating instrument. Backup protection of generator. Backup protection should always be given in highly rated machine like synchronous generator or alternator. If faults occurred had not been cleared by the appropriate protection scheme, then backup protection relays should be operated to clear the fault. Overcurrent relays are generally used for this purpose. Because the synchronous reactance of modern machine is often greater than 100%, the sustained fault current fed from the machine into an external fault is invariably below the normal full load current. The normal IDMT relays would not prove satisfactory because their current settings must be close to the full load and their time sitting short if operation is to be obtained, resulting in probable lack of discrimination with other overcurrent relays in the system. Further, the overcurrent relay would most probably operate for loss of field on the machine, disconnecting it prematurely. To overcome this problem, as it has become customary to apply an overcurrent relay in combination with under-voltage relay, the latter relay controlling the fault settings of the former is shown in the figure below. Why upgrade? Existing generator protection may require frequent and expensive maintenance, cause coordination issues with plant control excitation, turbine control, trip-on through faults, external faults, stable power swings, load encroachment and energizing, not follow NERC PRC standards protection and control. Exhibit insensitivity to certain abnormal operating conditions and fault types. Existing generator protection may not be self-diagnostic, lack comprehensive monitoring and communications capabilities, not provide valuable event information that can lead to rapid restoration. Part of NERC report comments on the August 3 blackout, not be in compliance with latest ANSI IEEE standards. Asset reliability, insurance, liability issues, see 37102, Guide for the Protection of Synchronous Generators. Improved sensitivity, loss of field, 100% stator ground fault, reverse power, negative sequence, overexcitation, improved security, directionally supervised ground differential protection, distance element enhancements, load encroachment blinding, power swing blocking for stable swings, new protections.